the very beginning, the machine age has depended on lubrication to keep the gears, shafts, and wheels of progress turning. Over the years, in agriculture, industry, construction, transportation, on the road and off, lubricants have played a critical role in getting the job done. And today, ever more sophisticated vehicles and machines demand ever more sophisticated lubrication products.
Engines, transmissions, axles, hydraulic systems, gear assemblies, and metalworking operations need specially formulated lubricants to protect critical components, provide reliable operation, lower maintenance cost, decrease downtime, and increase equipment life.
An effective lubricant reduces friction in engines and controls friction in transmissions, minimizes wear, acts as a heat transfer agent, inhibits corrosion and oxidation, removes wear debris and other contaminants, lessens the effect of temperature extremes on viscosity, and reduces noise. Obviously, reducing friction between moving parts is the most critical lubricant function in terms of increasing vehicle or equipment life. Even the smoothest surface such as this, when viewed microscopically, presents a landscape of peaks and valleys. These microscopic peaks, or asperities, are where the meshing surfaces contact and friction occurs. Friction acts to slow down or even stop the sliding action between surface asperities. The amount of friction generated depends not on the area of the meshing surfaces, but on the contact area of the microscopic peaks. Excessive friction can actually cause asperities to weld together and then break off as the parts continue to move. This wears down the metal surfaces and contaminates the lubricant with metal debris. As the number of asperities on the surface increases, the coefficient of friction increases. For each additional pound of force needed to move the parts, there will be an increase of frictional drag. The added power needed to overcome this frictional drag is unavailable as useful power to the machine, resulting in inefficient operation. This graph shows the effect of viscosity, speed, and load on friction. The graph can be divided into three areas which correspond to three different lubrication regimes: fluid film lubrication, boundary lubrication, and mixed film lubrication. These regimes relate to the lubricant film thickness in the contact area. Under fluid film, or hydrodynamic lubrication, the lubricant film is sufficiently thick to separate meshing surfaces completely, minimizing friction. This type of lubrication is present under conditions of maximum lubricant viscosity and minimum load. Fluid film lubrication fails, however, under shock loading, low speed, high torque operation, or low lubricant viscosity. Under these conditions, the machine operates in what is called boundary lubrication, and wear is prevented by using extreme pressure anti-wear additives in the lubricant. These additives form a protectant film of low shear strength, but with a high solid to liquid transition temperature on the meshing surfaces. This film, rather than continuous oil film, reacts with and coats the microscopic peaks on the surfaces of the components, protecting them from friction and excessive wear. Another type of lubrication, mixed film lubrication, combines the properties of fluid film and boundary lubrication, employing both a continuous lubricating film and a layered film to protect meshing surfaces. Lubricants must do their job under extreme operating conditions, conditions which conspire to break down the lubricant and reduce its effectiveness. This can happen in many ways. Premature wear and component failure can be the result of lubricant contamination, reduced or interrupted oil film, and inadequate levels or incorrect types of lubricant additives.